Geologists recognize a masterclass in mineral grain fracture, where others see a supernatural mystery. We're decoding the precision paradox to show exactly how nature uses internal stress cycles to snap solid rock with surgical accuracy. Rigorous science explains this laser cut better than any fiction. The Naslaa Rock Formation stands within the remote, arid expanse of the Tayma Oasis in northwestern Saudi Arabia. This diagram illustrates the scale of the structure. It is a single formation standing 20 feet tall and stretching 30 feet wide, divided by a gap so straight it challenges common assumptions about natural weathering. That challenge arises because the human brain struggles to reconcile the irregular scale of a multi-ton boulder with a separation gap measured in millimeters. Moving past the macro-scale mystery requires shifting our focus down into the microchemistry of the rock's composition. Resolving this paradox requires discarding the assumption of outside intervention and analyzing the crystalline grain structure of the stone. Explanations involving ancient technology or extraterrestrial lasers fail under basic geologic scrutiny. These theories ignore the intrinsic stratigraphy of sedimentary rock, which dictates how the material behaves under mechanical stress. Naslaa is sandstone, a composite of mineral grains cemented together in horizontal layers over millions of years. This composition makes the rock a candidate for mechanical weathering, where physical forces fracture the stone without changing its chemical makeup. Three specific forces, tectonic jointing, intense thermal dynamics, and Aeolian sandblasting, compounded over time to execute this bisection. Our investigation maps exactly how these dispersed natural forces execute a localized mechanical shear that mimics industrial engineering. The process begins with a structural geology concept known as jointing. Unlike a fault, which involves the displacement of rock, a joint is a clean fracture where the two sides pull apart without shifting. This diagram shows how historical tectonic shifts compressed the Arabian crust beneath the Tayma Oasis, applying steady pressure to the solid rock layers. Under this pressure, the rock develops a microscopic vertical plane of weakness internally to relieve the stress. Sandstone's layered composition causes these joints to form as straight vertical separations rather than jagged, irregular cracks. This microscopic plane established the mechanical path that set the stage for the physical split. This graph tracks the extreme diurnal temperature swings of the desert environment, where baking daytime highs contrast with freezing nighttime lows. These cycles drive the freeze-thaw process. Occasional rain and ambient water vapor seep deep into the microscopic tectonic joint. When water transitions into solid ice, its volume expands by 9%. As the desert temperature drops, the water trapped inside the joint crystallizes. This expansion exerts immense localized pressure against the interior walls of the rock. This pressure creates a zipper effect that travels cleanly down the pre-existing tectonic stress line. The mechanism mirrors modern glass cutting. Just as a glazier scores glass and uses thermal shock to snap it, nature used tectonics to score the rock and ice to apply the thermal wedge. The diurnal thermal expansion engine turned a microscopic joint into a physical bisection. While ice created the split, the interior faces of the fracture are incredibly smooth. To explain this finish, we turn to fluid dynamics. This involves a phenomenon known as the Venturi effect. This simulation shows how wind behaves when hitting the rock. As air funnels through the narrow gap, the constriction causes the wind speed to increase exponentially. This accelerated air acts as a high-speed sandblaster, firing abrasive quartz particles directly against the inner walls of the rock. Thousands of years of this targeted abrasive flow smoothed the interior faces to a finish that mimics industrial polishing. At the base of the rock, Naslaa presents a second illusion. The two massive halves appear to be levitating on small pedestals. This is the result of a desert geomorphology process called saltation. During saltation, wind bounces heavy, abrasive sand grains along the ground. Because of their mass, they rarely lift higher than a few feet into the air. This constant barrage concentrates erosion on the lower portion of the stone, sculpting the narrow pedestals we see today. The mushroom rock effect is a direct record of localized, ground-level erosion wearing away the stone's foundation. Because Naslaa is the product of physics, similar geometric precision exists in other formations globally. Mushroom rocks are a common global phenomenon, produced by the same saltation forces seen in the Saudi desert. Hexagonal basalt columns provide another example of mechanical stress creating geometric symmetry. Cooling mechanics force these columns into hexagons, just as thermal cycles forced Naslaa into a straight bisection. Nature operates as a precise architect, governed by the repeatable laws of physics. Ancient people also observed this formation, leaving petroglyphs on its surface thousands of years ago. The sequence is mechanically consistent. Tectonic jointing established the path, thermal expansion executed the cut, and wind-driven sand polished the finish. Naslaa is a masterpiece of mechanical weathering, not a supernatural anomaly. Scientific literacy provides the tools necessary to analyze these structures without relying on viral misinformation. Structural geology reveals a reality defined by mechanical rigor that fictional shortcuts cannot match. Dive deeper into the mechanics that shape our reality. Click the subscribe button, activate the bell, and see you in the next scientific investigation beyond the boundaries of reason, only on TEMBODocs.